So shall I start, Santosh?
Yeah, just wait a minute.
All right, okay.
Okay. So welcome all to another session of SD skills. And today we'll be discussing data structures and algorithms. In this, we'll be discussing string permutations, bitwise operations, and the reservoir sampling. So Ajay will be presenting the string permutations. Okay, so Ajay, yeah, you go ahead.
All right, okay. Thank you, Santosh.
Thank you.
Hi, guys. So basically, this is the problem, permutation problem. It's a very famous problem where which says given an array, numbers of distinct integer, return all the possible permutation. You can return the answer in any order. So basically, it asks us to find the permutation for a number. It could be string also in case. In here, the example is 1 2 3, and these are the possible permutations for this particular array. So the objective of this problem is actually not the permutation problem, but we will try to find out a pattern which can be reutilized somewhere else. So this pattern, I am calling it template include, backtracking, and exclude. So basically in that backtracking examples, in these problems, we use the same kind of pattern, and that pattern we will try to explore in this problem. So so um, for starting, I will actually take the example and I will share my another screen. um, Share screen. Okay.
Yeah, for sharing another screen, you might have to unshare this
Oh,
and again share it. Yeah.
okay. All right. Okay. So everybody can see my screen, I think, right?
Yes. Yeah.
All right. So let's say we have, let's not take 1 2 3 because it's number. I want to use that for using index for simplicity. So I am going to take it as ABC. Let's say this is the string and we need to find out all the permutation, and we are only talking about template, include, backtracking, exclude. So as per this approach, basically what I'm going to do is I will fix none here, and then go to the another level, start another level, where since I fix none, it remains A, B, and C. After that, I will fix A, and then since I fixed A, then I can go ahead and swap B with B, because I always start from itself, from the zeroth index. Um, so A was already fixed, so I swap B with B and C. So right now I meet an exit condition. So this is one of my permute. So what I did basically, I did swap A with A. Here I swap B with B, and then I go backtracking. I swap them again, like re-swap that to nullify the effect which I did that before. I swap that again, it goes back in here. Then since I swapped B with B, now I swap B and C. Oh, sorry. And then basically in here also I should make, then I fix C. Since it meets the exit criteria, this also exits, and um, this is also one of the permute. I go back, and similarly I do the same operation with B now. So I should actually take this a little bit here. I go back in here, and then I start doing this for B. Let me take it a little far. Okay. So here it's the turn of B. So we say B, A, C, because we swapped A with B, A with B, and then we fix B. We go underneath the same way, this same level. Mm, And then B, A, C. I will draw it real quick now. And then B, C, and A. Swapping these. So this meets the exit criteria. So these are also another permutes. Similarly for C, A and C. So we come here, we say C, B, A, and maybe here. Okay, it's doing something. So this is going to be C, B, A. In this, we did this, and then C, A, B, C, A, B. In here, basically we swap B with B and B with A. So basically this is what we have the approach for backtracking to find the permutation. So now we have these are the permutes which we need to find out.
Yeah, one question, Ajay.
Yes.
When you say exit condition, what do you mean by that?
So recursion always will have an exit condition. That is what we're with which I am talking in here.
Okay.
So as soon as we start from L, let's say this is L and this is R, L and R, and L is the starting of it and R is the end of it, and we will always let's say another ith index, and we will keep on moving I from zeroth index to R minus one, let's say R size R minus one. And then we will keep on doing the operation for entire tree
Okay.
at every level.
So when you end up to that index of this array, so that is your exit condition. Okay.
Yes.
Yeah, makes
So,
sense.
so basically exit condition is nothing but, because I am going from the left to right, I am keep on incrementing at every level 1 plus 1. So I mean L plus 1. And as soon as L is equals to R, it means I have met the end.
Yeah, perfect. Thank you. Yeah.
So Ajay, the exit condition is the bounded function, right?
Yeah,
Bound,
it is the bounded function or boundary. Like,
bounding condition or something.
yeah,
Bounding.
Yeah, boundary condition. Yeah.
yeah,
Eh,
base condition,
we call it.
exit condition.
Go ahead.
Yeah, we when we do the recursion, we talk about base condition, exit condition, and boundary conditions, right? So in here, what will be the exit condition to come out of the recursion? Otherwise, if we don't do that, it will not have a return, which is
Yeah.
which is basically is the exit to push into the result also, or print the permute.
Or reduce the number of combinations or tries.
Uh,
Like if
yeah,
you have six permutations, if you want to have some condition is C should not be last or B should not be last, then we'll use that as exit condition so that we don't have to go till the end of the tree.
No, I think
no,
that's
no, no.
exit
So,
condition will
so
be like whatever permutation you have obtained. If the length of that permutation is equal to original length of the array,
exactly.
then that will be because permutation you are just changing the position, not the quantity, right? I mean the
Yeah.
number of elements.
Okay, got it, got it. Yeah.
Yeah, or either that way, or if we are at the right index, then also I
Okay.
think we can say that we are done, right?
Yeah, because you have finished the entire what do you say
Yeah.
traverse the
So as Shashank said, length of the length of the current permute, whatever we are working on, if it matches with the length, uh, like uh, the measurement is done with the counter, basically L and R, which I'm taking here. So as soon as we reach to the end of the string, it means we are done with the permute. This current is the length 3. So we will push this.
mm.
Yeah, I think it's clear now, right? Yeah.
And one more, you swapped A with B, A with C. Now B with C, that branch you are not, or is it taken care inside only, right? Somewhere. I mean,
Well, he has just indicated few of them, I think, because if you draw the whole recursion tree, it will be big. It won't look like.
Well, I drew the all combinations, but I did not write it in here saying, well, like say C is C with B. All these I did not write. I just kept on, yeah. But the idea is we are including and excluding. In between, we have a recursion call. That is what the template is. So now I want to draw your attention to how we can draw a template in here. So basically, I mean, is there any other question? Mm.
Oh, I think we are good. Yeah, go ahead. Yeah.
All right. Okay. So basically, okay. So let's code for it. I would say, shall we write little pseudocode? Okay. Let's write pseudocode rather than coding. All right. Okay. So what it says is basically we are going to swap include, which I am counting as include. I'm going to swap A with A. At another level, I will swap B with B. And at the end, I will, as soon as I meet the exit condition, I will push that element in there. So basically the approach in here, first of all, we are going to, let's talk about for loop. So we are basically iterating through entire length of the string. Let's say str dot, let's keep it in sync with. And then, as we said, we will swap nums with L and I. This is the include portion. And then we have a back recursive call to, let's say this function is permute util. And then I am going to pass, let's say this as I should be quick. And at every level, I am going one ahead. So I will go L+1 and R, which I decided L and R. And then I will, once my call finishes, I will reswap those. That's it. So this is the template which basically we'll be using all the time. So now since we have every one thumb rule is whenever we have a recursion, we should always think about exit condition, base condition, and boundaries. So here we need to have exit condition. When will you say that okay, the permute is um, permute is done? So for that, I will have an exit condition which is on the top, but I am going to write it in here. So let's say if L is equals to R, at that time, let's push it into the result. And that number, because I'm doing in place swapping, so that number will be pushed back. Push back the state of nums at that time and return. It will break the recursion. So this is what my exit condition I was talking. All right, okay. So this is the template. Template has include. Include can have multiple forms. Here it is swap. It can have some in some problem. It will be having sets in some other problem. In binary watch, it is a different problem. So the swap is the include the mean swap in here in this problem, and this is of course recursive call, and this is exclude. So whenever we have a recursion, we will definitely see that what all the exit condition boundaries as well as base conditions. So at that time, this will also come into picture, and that's it. Uh, this entire pattern is being followed by 13 problems. So I actually can share those problems. So I will actually take you back to my desktop now. Let me share screen again. So guys, any question about? Um,
Regarding time complexity,
okay, so let's see the time complexity. I mean, my focus is not the time complexity in the session, but let's discuss about this. So the time complexity, if you say, let's find Tn time complexity, which will be nothing but um,
n into t of n, right?
O into 1, which is nothing but the include portion of it, right? And then there will be recursive call, which is nothing but T of n minus 1, right?
Yeah.
Because we moved 1,
So,
and plus O1, which will be again nothing but your exclude.
but tn minus 1 is running n times, right? Because it is under the for loop.
Yes, of course. Yes, of course. Yeah, you're right.
N into t of n minus 1. Okay.
Yeah. So yeah, n into n factorial.
It will be too much.
Well, like as I said, um, the main focus I want, because see the thing is with one template, if I can solve 13 problem, I will definitely do those problems. So that is what intention is like. And the motivation about this entire exercise was we were discussing in Leetcode problem in morning. And yeah, like we came across this and thought of sharing this with everybody.
Yeah. Gotcha.
So let me share my screen. Continue.
So one question is, how many number of how many, what would be the result, size of the result? Is it n into n factorial?
uh,
3 factorial will be there, right? Because three numbers are there. That's why the size of the result will be 6. 3 factorial.
3 factorial.
Because those many
So
permutations can make out of.
so then complexity should be just n factorial, not n into n factorial. Is that correct?
Yeah.
If you short the recurrence relation, it will come out to be n factorial.
Yeah, well, okay. So the number of permutes are n factorial, but if you want to print that value, the iteration will be another n. So that is where for the printing it is n into n factorial.
N plus.
You mean to say that print each character? That's what comes in n, or
Mm,
Yeah, he's saying that for printing each character is running.
But you will print after you are done with this, right? So it is not going to be, it will be plus n, right? Over
Yeah.
n factorial plus O of n. So n factorial is dominating. So it should be O of n factorial, correct?
Yeah.
I think that is the max you can do in this permutation, right? You have to have an O of n factorial.
Yeah, n factorial. That is the max.
You cannot
Brute force
optimize
will
that,
be
yeah.
that only. N factorial,
I
right?
don't, because that's a pattern, right? So that is, I think, that is the way it will be done. Okay, yeah, go ahead, Ajay.
okay. So I think you can share, see my screen, right?
Yes.
All right. Okay. So okay, just a minute, please. So we were talking like, okay, how and why we decided to do that. So here on the internet also a couple of people are talking about this. I think it is a good move. So this is the entire list, guys. If we have solved one problem, we can uh, shoot all these problems. So please check that. And another another post also I saw where people are talking about this. So here is another. It's saying classic backtracking problems, approach and techniques. So yeah. So this is the background of it. So one can solve multiple. I will share the content of the um, the file later. But let's real quick write this program and finish it off. So basically, we are supposed to find the um, permutes. So let's write it real quick. All right. Okay. So just a little variable declarations for ease. So real quick, I want to check if it is valid input parameter, but I don't want to explore too much in there. So let's go get going. I will also check for early exit conditions where relatively lesser complex logic. Let's say num size is equals to 1. All we gotta return is end result. So, okay. So now let's come to our approach. Our approach is nothing but include, I mean, you can give any other name, better name if you don't like this name, but I am going with this. So this is my approach. In there, uh, I am going to introduce a utility function, little bit modularization, where I am going to, okay, there is no need to have, so what I'm going to do is I am going to make a void function where nums are passed. I already give a start. So let's say integer L is equals to 0. Integer R is equals to nums size -1. This is I pass in here R, and I also pass results. So now my this function is complete. Return results. Let's say all results. Okay, actually, let's say them permutes. So this my focus in this function is gone. So now I will only talk about my approach. So in that, as I said, I will go include exclude. So I am just copy pasting that. We said we will have exit condition, which is must for recursion. Say it must. Okay, so for integer I is equals to, so this is a different function, util, right? Same. Then I have, let's say integer L itself, we can name integer R, and then of course a result. So we pass this, and this is my auxiliary function, which is private. So now I start from L, and I is less than equal to R I plus plus, and then swap nums L and I, permute util, which is a recursive call where nums L plus 1 and R. We will move 1 and -1 which we thought, and then we will do this again, what we did one step before. So that's the whole include template. As we said, we will include exit condition. So that is L is equals to R. Oh, sorry. L is equals to R. That time push that into state nums state. Okay, that is enough. Return. All right. Okay. So let's revisit one more time. Okay, no, sorry, I did not write the swap. Let's write auxiliary function real quick, which is nothing but vector of int nums integer I integer j. Integer temp is equals to nums I is equals to nums j nums I, sorry, j equals to 10. So okay, ij, okay, I think, all right, okay, let me revisit real quick and let me go through once again. So we already talked about our main function, not main function, but the permute function. We may build another private function, which we calling it permute util. After that, I have my template. That template I used for building up my logic, which we discussed. And after that, I also have to include the exit conditions. One auxiliary function swap array I wrote, a small function, and that's it. I am going to check like little syntax real quick because I am seeing a couple of issues.
Yeah, I think overall the syntax looks okay, right? Yeah.
The return type of permute util function will be void.
Yeah. And that was the
Oh,
motive.
yeah, yeah.
There wide. I mean, we all do this mistake, right? We
Right.
jump into as soon as we done.
Oh, that's fine. Yeah.
So yeah, I'm trying my best.
Yeah. Okay. So, Shashank, the way you are saying O of n into n factorial, it is because on line 17, he's running the for loop, right?
Yeah.
Yeah. I think that makes sense, right? Yeah.
No, I think a result of n into t of n plus 1 will be n factorial if we solve that equation.
Okay. Yeah. Okay.
All right, guys, let
You,
me
you want to run it?
let me see
Okay.
how it goes. All right, okay, we have some,
Oh, S,
Perm
S,
or something. Okay.
mm,
SS.
yeah,
S.
result. Let me see if there is any other result. No, I cannot see like this. Okay, let me run it. If there was. All right, okay, so we have some issue. Okay, what one, and then L is equals to I.
L equal to r minus 1 or 1. Will L equal to r minus 1 or it's fine? I mean, index L is starting from 0, right?
Yes. Here is the issue, I think. No, that is not. Size L and R. Okay, then I went in here. L is equals to
Yeah, that's fine. I think because overall the whole
no,
algorithm is exactly what was expected, correct?
yeah,
There
But
might be some minor
yeah.
debugging issues, but that's okay.
he is
Oh,
not
the
pushing intermediate.
compare operator, yeah. Even the num size also first one, line number 32.
Yeah. Okay, so
Okay, cool.
yeah,
Yeah.
there is mistakes. So it's a good idea to see after completion line by line to see, okay, did I make any mistake? So I
Right.
did.
Yeah.
Okay. So yeah. So this is what the basic idea is. Idea is we can break down these problems into this, and all it does is in other problems which we will like maybe like in future we will talk about is just adding up couple of more Legos, like little bit components. For example, duplicacy check. We will introduce duplicacy check, and then we will have some more boundary conditions depending upon the nature of the question. So yeah, this is it.
Another base case that num size 1 not required, right?
Num
Means
size one is not required, yes, and that is why early exit condition is taken care
no,
of.
no, but the loop also will take care, right? The recursive also is taking care, I think, right? Because if it is 0, if L is 0,
Oh,
R is also 0,
yes,
it
you're
goes
right.
to it is going to push to the result anyway.
Yeah, you're right. But this is what I try to do in interviews. I mean, I am sure everybody we are preparing for interviews. So in there, it is a pattern, and it actually breaks down into sub problems. And it also tells like, okay, you are taking care of validations, you are taking care of defaults, you are taking care of early exit condition and different approaches. So I just follow this. Otherwise, you need not to even write that much. Just write um, write the function and get going like that.
Yeah, this is a very useful pattern. I agreed. Yeah.
Any question, guys? Please tell.
Yeah, I think we have gone through all the questions when you are actually working on it. Yeah,
Okay.
that's cool.
All right.
Yeah,
I will send some stuff also like on this, some material which will help
sure.
on the chat.
No problem.
Thank you, guys. I will send.
Thanks.
Thank you. Yeah. Thanks, Ajay. Yes, Sapul, do you want to go next?
Yeah, let me share my screen.
Please, go ahead.
Mhm.
Yeah, thank you, Ajay. It was good.
Thanks. Thank you.
Let me get my chat too. All right. As you guys can see the bitwise operation, right?
Yes.
Okay. Oops. Hello, everyone. My name is Safal. Today we're gonna go about bitwise operation. So this will be a little different. It'll be we're gonna shift away from Leetcode for a little bit, and we're gonna focus on fundamentals, right? For most of us, it's probably gonna be a refresher. Even for me, while I was preparing for this, it was a refresher with all this bitwise operation. But we need to know the fundamentals before we tackle a lead code problem. Okay, and at the end of the session, we will tackle a lead code problem. Focus fully on bitwise operation. So our agenda for today is briefly talk about what is bitwise operation, right? We'll review each of those bitwise operators, and we will also review each of those bitwise shift operators. We'll review bit masking, and we'll review a lead code problem, a number of 1 bits, and we'll do a Q&A and feedback at the end. All right, so what is a bitwise operation, right? So bitwise operation is nothing but basically we're doing a bit manipulation, but we're using bitwise operators or shifting, but we're doing it at the binary digits or the bits of an integer. Let's call it that way, right? We're just doing the manipulation of those bits and using our operation. That operation is called bitwise operation, right? So for example, in this second point where I says shifting left moves all bits in a binary number to left. So we have a binary number like 0, 0, 0, 1, 1, 1. If we do bit shift to the left, the result will come out 0, 0, 0, 1, 1, 1, 0, 0. And we'll talk about how that is and whatnot. But basically the gist is that's what bitwise operation is, right? All right, so few of our common bitwise operators, first one is bitwise and, bitwise or, right? The third one is bitwise exclusive or, and the last one is bitwise not. Um, Now let's talk about and bitwise, right? And I'll go straight into the table, right? So what happens is with bitwise and, let's say we have 2 bits, 0 and 0, right? If I'm doing 0 and 0, the result would be 0, right? 1 and 0, the result would be 0. 0 and 1, result would be 0. 1 and 1, result would be 1. And the trick that I use to memorize this is it's similar to multiplication rule. If you look at it, 0 times 0 is 0. It's very simple. It's actually easier to memorize bitwise and because it's so similar to multiplication rule, right? The second slide is bitwise or. Now, or a little trick, right? Same, the only difference is 0 or 0 is 0, 1 or 0 is 1, 0. So if you notice, it's not multiplication. The trick to memorize this is similar to addition rule, except 1 or 1 is 1, except 2. Otherwise, it's very similar to, like we're adding 0 plus 0 is 0, 1 plus 0 is 1, that thing. But that's how I use this trick to memorize it, right? All right. Second, the other is we have bitwise exclusive R. Now with exclusive R, same concept, right? 0, we're basically doing the operation in 2 bits right now. So 0 exclusive or 0 is 0, 1 XOR 0 is 1. So the trick to memorize here is it's very similar to addition rule, but except 1 exclusive or 1 is 0. It's still tricky. So the other one was 1 or 1 was 1. Here is 1 XOR 1 is 0. I know it's a little tricky, but those are the few tricks that I use to memorize this table. All right, so bitwise not, it's simple, right? So basically, it's like a tilde notation. We're just reversing it. If it's a 0, the result is 1. If it's a 1, result is 0. It's reversing each binary digit and an integer, from 0 to 1 and 1 to 0. Now we'll talk about bitwise shift operators, and we'll mainly focus on these three shifts. So the first one is bitwise shift left, bitwise shift right, and bitwise unsigned shift right. Okay. Now bitwise shift right. Let me get my pen. All right. So shifting left moves all bits and a binary number to the left, right? So here what we're saying is, so on this in the above example, the trick to memorize is, so we're doing 2 bits to bit shift left by 2. So we're saying on the above example, 2 bits will fall off on the left, and we're adding 2 zeros on the right. So 2, right? So I'm gonna grab these two. What I'm doing is, if you just, focus on this 0, 0, 0, 1, 1, 1, they're still there, right? 0, 0, 0, 1, 1, 1, and I'm adding these two right here in the end, and the result will be 0, 0, 0, 1, 1, 1, and last the 2 zeros, right? This one is actually easy to remember, bitwise shift left. Now, if you notice, the other advantage of this is this is binary, right? So what's happening here? So this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2. Every time I'm doing bit shift to the left, if you notice, I'm also multiplying a number by 2. This is this is basically really important, I would say, concept. Just enhance our performance significantly, because all we have to do is just each shifting to the left, and like you notice, it multiplies a number by 2. And trick to memorize is, when the bits falls on the left, we're adding 2 zeros on the right. Okay. Now let's talk about bitwise shift right. All right. So shifting right moves all bits in a binary number to the right. Right. So the trick to memorize. So on the first example, let's see, we have 3 bits in a binary number, bitwise shift right by 3. 3 bits falls off on the right, and we're adding most significant bit leftmost bits on the left. So what's happening is, so let's see, so this 3, right, we're taking them off, and now what's remaining is, if you notice, 0 1 0 1. So 0 1 0 1 still there, and we're adding it on the left. Now, not the other point is, we're adding the most significant bit. Now, what is the most significant? This is the MSB, right? The leftmost bit is always the most significant bit. We're adding the, not necessarily 0, but we're adding the MSB. MSB on this first example is 0. That's why we added 3 zeros on the top. On the second example, if you notice, MSB was 1. So when we did this bit shifting right by 3, okay, we took off 3 zeros. Now the remaining is 1 0 1 1 1, 1 0 1 1 1, but we're adding number 1 in the top, because our MSB was 1 on the second example. Okay, a little here and there, but that's how bitwise shift right operator works, right? Now, if you notice, also on this case, same concept, right? Now, this is binary, 2 to the power 0, 2 to the power 1, 2 to the power 2. Now, each shifting to the right. If we're going to the left, we were multiplying by 2. But if we're going to the right, we were dividing by 2. Okay, so each shifting to the right, we're dividing a number by 2. Another key concept that we need to remember on this. Okay, now we'll talk about bitwise unsigned shift right. Right. So shifting right is the same concept as the earlier bitwise shift right, but the trick to memorize is, on the for example, 3 bits falls off on the right, and we're adding 3 zeros. we were adding the three MSBs on the left. On this case, it doesn't matter. It doesn't maintain the leftmost bit value in your right shift. So what I'm saying is, um, okay, same. Let's take it this example. We're doing bit shift, unsigned shift right by 3. We'll take this 3 off, right? Same concept, 101 was there, but instead of looking at this MSB, we don't look at it. We just say, okay, it's all zeros, and we just add zeros in the top. That's the only difference. Same concept as earlier, each shifting to the right divides our number by 2. Okay. Now, let's see. Another key topic is, now we'll talk about bit masking. Okay. Now, bit masking, we use bit masking, and you'll see where do we exactly in a Leetcode problem. We'll have to use a bit masking to solve it, but it's basically we'll create a integer we use it to select or alter a set of bits in another number, right? That's so our mask will be, okay, I'll have a binary number of bits, and I'll use it. So if I need to get a certain bit, or if I need to alter the bit, if I need to change 1 to 0, 0 to 1, I use my mask to do it, right? It's very helpful. So for example, what I'm saying is the third bit, is the bit 1, is the third bit set in the binary number, right? So this is our number 11101. What I'm saying is the third bit is looking at this particular number 1. Is it set? It's third bit set in the binary number. Is it when I say set, I'm saying, okay, is it 1, right? Of course we know already 1, but we have to prove it, right? So the technique is we'll create a mask with only that particular bit set and use the AND operator. So this is my mask, right? So what I did was, okay, everything is 0 except that third bit that I'm checking, and I'm using the AND operator. And if my result comes 1, then yes, the third bit is set, right? That's one technique of one, I guess, area of bit masking, selecting it, right? And next we'll talk about how to alter it, right? Sometimes we have to edit, update. All right, so next technique is assign the third bit, the value 1 in a binary number, right? So if you, here, this is my binary number. Now what I'm saying, okay, this is my number. Now, right now the third bit is 0. So we will need to change that to 1. How do we do it, right? Now the technique is we'll create a mask with only the third bit set and use the OR operator to assign the bit. So here's my mask, all zeros except that 1, but instead of AND, I'll use the OR operator. This is if I need to set the bit, assign the bit. The result will be 1101. Now the third bit is now set to 1. Okay. Now once you get a hang of it, this is very simple actually. All right, the next example is, now earlier we did we assigned 1, but now we'll assign the third bit the value 0, right? So right now we have 1. I'm saying, okay, now let's change this 1 to 0. So the technique is create a mask with all bits set except the third bit and use the AND operator to assign the bit. So AND operator, everything's 1, right? Except that particular operator, third bit is 0. That's our mask, and we'll do an AND operator, and it'll be 0. So the third bit is now set to 0. Okay. All right. Let me see. All right. So now these are the based on all the concepts that we just studied about bitwise operation. We'll review a problem, right? But before I go to the problem, I know I threw a lot of information at you guys. Do you guys have any questions?
Yeah, so you were explaining the unsigned shifting right and left. So that is the only difference. The difference between both of them is only on the MSB, you are actually putting zeros when you are doing an unsigned shift right, right?
Right. So my regular shift right is I have to check my MSP, right? 0 was 0, 1 was we're all ones, but the unsigned shift is we'll still do the right shift, but instead of checking the MSP, we will just add zeros. That was the only difference. So here 1 didn't come in account. All I said was, okay, we'll take it off, we'll add zeros. That was the only difference.
Okay, and the operator that you are going to use, I think, is this a Java sort of operations?
Yeah. Yep.
Oh, 3 greater than, okay.
Yep.
because I never saw that in C++. Okay, so I was just wondering what is that.
Yeah.
Okay, so it's the difference between the logical shifting and the arithmetic shifting, what we call in C++.
Okay.
Okay, makes sense now. Cool.
Yeah.
Yeah.
In the C++, is it that arithmetic is assigned one?
Well, either of it, right? So I think I'll have to check, but either of it, one of them should be like this with 0 zeros, and other should be 1 1 1.
Okay.
All right, guys. If you don't have any questions, we'll review this problem on Leetcode. Okay.
Sure, yeah.
So here, our problem says, okay, number of 1 bits. Write a function that takes an unsigned integer, right, and returns the number of 1 bits it has, right? Unsigned integer means, so if it's an unsigned integer, means the integer cannot be negative, right? If it's a signed integer, means integer can be negative. Uh, Yep, unsigned is it cannot be negative, and signed is it is an integer that can be negative. So basically, how many Java, like we have 32 bits, right? So if we have, if we say it's an unsigned integer, um, then it has a higher range of positive values, and if it's a signed integer, then it has lower positive range, right? But let's focus on the question. So basically, if it takes an unsigned integer, then we'll have to return the number of 1 bits, right? So what it's basically saying is, so this is a 32 bit, zeros and one. There's 32 of them, and we're basically saying, okay, how many ones are there in this 32 bit, right? And here, same thing, 32 bits. How many ones are here? It's 1 1 1. Here, 32 bits. How many one? It's there's 1 0, so there's 31 ones. That's all I was asking. Okay. Now here we will use bitwise operation to do it. Uh, so the way we'll do it is, so our logic is very simple, right? So we will check, we'll use bit masking and everything, but we will check each of the bits of the number from the right. And if the bit is 1, we'll add it to our bits counter, okay? And at the end, we will just return our bits. That's all we're doing, right? And obviously, to do this, we'll have to understand the concept that I explained to you earlier, right? So, but we'll review the same concept here again. So what happens on this code is, let's say, okay, we have, I believe it says the constant is 32 bits, okay? But let's say we only have, because we don't need to, so it's a 1011, right? That's 11 in decimal. Let's say I only do like I is less than 4, right? Because the rest of them is 0 anyway. So we'll just focus on these 4 operations. What happens, line by line. So what happens is, if n is 111, so binary 1011, right? So we loop until 4. That's let's say if that's, I'm saying if I change this to 4, right? Just for the explanation, but we'll change this to 32, to pass it all these test cases for Leetcode. So what happens is, at first loop, if n and our mask is not equal to 0, then we'll increment our bits. So what I'm saying is, okay, n is 1011, right? So my mask, I created 1, right? So my mask, which is 0 0 1 1, 2 to the power 0 1, everything is 0, right? So if I do an operator with my mask in n and mask, then it comes out 0 0 0 1, right? So if it's not equal to 0, right, then bits plus plus. So what I'm saying is, here, if it's not, if it was 0, then we would have said, okay, this bit was actually a 0. But if it's not equal to 0, then we know actually, okay, this bit has a 1 in it. That's why, since I found 1 1, that's why I will increment bits plus plus. That's all I'm doing. So remember how I use my mask? I use mask to check if the certain bit is 1 to 0. And this is exactly how I did. I'm using the same logic, same technique here, right? That I explained earlier. So, okay, this is 1. Since it's not equal to 0, that's why I'll increment my bits plus plus, right? Now, what I'll do is I will shift my mask, left shift my mask by 1, right? So after that first loop, after the if condition exists, since the bit mask left shift by 1, the m will bit shift left by 1. So it'll be 0 0 1 0, right? Now at second loop, now we'll use my same now. The binary number does not change. 1011, 1001. Okay, it's the second bit set. It says yes, it is set. Then since it's not equal to 0, we will increment our bits, right? We will change our mask. Okay, and our third loop we're checking is the third bit set. Since it's now if I do 0, 1, 0, since it's equal to 0, we won't increment bits. So it's like nope, this is 0, you know. And then mask will do the same thing, you know, will left by 1, mask will be like this. And on a fourth loop is this for a fourth bit set. Yes, it is set, you know, 100. It it actually returns how many bits? Oh, it actually returns bit 3, and that's how this number 3 comes as an output of on this particular bitwise operation. And but another thing, if you also notice, is the reason why we are so much focused on bit masking is what's the time complexity on this, right? How many loops are we making? Like this time complexity is O of 1. O of 1. Why? Because we're not dealing with decimal, we're using bits. So the runtime actually depends on the number of bits in this n, right? So on my example, my n was 11, right? So how many bits are there? 32, right? So doesn't matter what the decimal value is. The bit number of bits is constant. There's always going to be 32 bits, you know, no higher, no lower, right? So the time complexity is constant. Space complexity, we didn't use any space, so O1. That's why we're really it's, you know, knowing the bit wise operation from fundamentally is so important because it has so much it's so much efficient in problems like this, right? All right,
I think
that was all my question, guys. Please let me know if you have any questions.
I think time complexity should be log n based too, right? I mean, those many number of the bits will be there for n.
No, because my the, the doesn't matter. My number of bits doesn't change regardless of the size of n. So n could be any number, you know, but it'll still be 32 bits. So my operation this doesn't change regardless of the size of the value n. Yeah.
Then
Hmm.
Yeah, he takes that advantage of 32. Yeah.
Hmm.
Yeah, that's true. That's good. So in this Hamming weight, I think there is other way also of doing it, right? So this is the one way you do for the masking, because you are going to each and every bit and checking it, right? So you'll have to do for all the 32 bits, in spite even if they are zeros, right?
Right. There's I think there's a certain efficient way to do it. But the reason I brought this problem is okay. Since it's focused on bitwise operation, and I just wanted to kind of
Okay.
solidify that knowledge. You know how we can use bitwise operation on a problem on Leetcode. And yeah, and there's even with this, there's I think a few ways you can tweak it and make it more efficient. Yeah.
Right. Yeah, so you can do an early termination when you don't find anything before that, right? Yeah, okay.
Right. Right. Yeah, guys. Yeah.
yeah, it was nicely presented.
Right.
Yeah, very nice. Safal, can you please share this PPT if you don't mind?
Yeah, I will put him on a
It's
Google Drive and I'll share the link on the.
all right. That works. Thank you.
Yep, no worries. Yeah, I put nice tricks on you.
Yeah, they
Yeah,
are useful.
yeah, it has entire summary, so it's a like
Uh-huh.
really good material when we are revising.
Yep, yep, I agree.
So yeah, thank you.
Yep.
In the Python, like the is it the same thing? It has the same the arithmetic one. I was trying afterwards. I did not debug, but like, is it same thing? The shifting operation has that signing thing.
Yeah. It's two signs are there. This is for right shift and this is for left shift.
Okay, you also follow the same. Mhm.
Yeah. But in Java, it's three was doing. I didn't get till now. Like,
That's for that unsigned and signed, right?
oh,
Yeah.
Yeah, but the fundamental concept of operations should be the same, right? Regardless of which language.
Right,
yes, yes.
right, right.
Yeah.
Couple of notations.
Yeah, the examples was good. I always used to get confused in some of the areas. Now it's clear.
Okay, that's good. I'm glad the session was helpful. All right, guys. Well, I'm gonna stop my share. Thank you again.
Thank you. Thank you.
Mhm.
Great. Yeah, good. Yeah, Abhishek, would you like to go ahead?
Yeah, yeah. Am I audible?
Yes.
All right. Hi everyone. I am Abhishek Jha, and I am just a pre-final year undergrad student. And today we will be discussing a topic called reservoir sampling. So let me share my screen. Okay. So just take. We will be taking one question, and then we will be approaching it in such a way that we come across the topic reservoir sampling. So what is given is we are given a singly linked list and we need to return a random nodes value from the linked list. And each node must have the same probability of being chosen. So let us imagine we are given a stream of n integers where we don't know the value of n. So the value of n can be very large. So we don't know what is the actual value of the n beforehand. So how we will approach this kind of problem if it comes in the interview. So the first approach which will come into our mind is copy the stream of integers in array or uh, or any container. So first we will iterate through the stream, and then since we don't know where it will break, or since it is given it is singly linked list, we know that it will break when the next pointer of the singly linked list will point to null. So till then we can copy all the values in the linked list in a vector or any container, and at last we will know the final value of the size of the container. Now after uh, we we copy the value, what we can do is we can generate a random integer from the range 0 to n minus 1, where n will be the size of the container, and then we can return the value of the particular index, the value at the particular index which we generated using the random function. So that's all right. We solved the problem, but let's analyze the complexity. So since we are copying the value in a container, or we can say a separate container, copying into a separate container, we are taking an extra memory space of O of or big of n space. And then, but since we know that the random function which generates the random value takes a constant time, so really doesn't matter. So the random function will just take a constant time. So the only problem here which we are facing is we are taking an extra memory space while solving this problem. So to optimize the space complexity here, we study a separate kind of algorithm or a family of randomized algorithm, which is called as reservoir sampling. So what really is reservoir sampling? So reservoir sampling is a family of randomized algorithm for randomly choosing k elements from a stream of n items, uh, where the value of n can be very large, and we really cannot fit the amount of numbers in the items or the stream. So this is why we study this kind of randomized algorithm. So, and also we need to keep in mind that the probability of being chosen of each of the item in the list has to be same. So in the first approach, when we were generating a value uh, using the rand function, it was a value between 0 to n minus 1. So we can see the probability here. Okay, so there was no problem with the probability part. So the probability was 1 by n as we need it. So since we were generating one value out of 0 to n minus 1, and the total number of stream size was n, so the probability of choosing each of the values in the entire stream was 1 by n. So that's not a problem, but we need to keep this in mind while choosing any number from the stream. So now let's come to the next approach, which is reservoir sampling. So here we need to optimize the space complexity which we are using in the first approach. So imagine the stream is of size 4, and the values in the stream is 1, 2, 3, 4. Let's take this as an example, and then I will be taking some of the variables and then explaining how we are calculating the value. So at first, since we don't know the size of the container or the stream, so we will start iterating from the stream of the integer. So let's suppose I am iterating in the integer. Now, also I need to keep in mind the probability of choosing each of the integer in the stream has to be 1 by n. So and the index of these values will be 0, 1, 2, 3. All right. So when I start iterating from the 0th index, I will call the random function which works in constant time, and then I will generate a value from 0 to the number of iterables in the container. So for index 0, I will have only one value for the random function to select from. For index 1, I will be having 0 and 1 to select from. For index 2, I will be having 0, 1, and 2 from select from. And for index 3, similarly, I will be having 0, 1, 2, and 3 to select from. So in the for loop, I will just call the random function, and the random function has to be from the range 0 to the number of items, which will be taken care of when when we will be implementing the function. And then I will check if the value which was generated in the rand function comes out to be the exact value of the index at which I am currently am, then I will just choose that particular index as the answer. So for example, if I am at index 2 and the random function generates a value 2, so we know that now we have to select the value which is 2, which is at the index 2. Similarly, if I come to index 3, and if the random function generates a value 3, then I will select the value which is at index 3, that is 4. Now, uh, that's okay. So,
But if it doesn't come at that index, right?
yes.
So
Uh,
what value do you take in that case then?
okay. So in that case, since we know when we are at index 0, we have only one option to choose from. So at first, I will be assigning the answer variable to the value at index 0.
Okay.
Does that make sense?
Yeah. Okay. No
Okay,
problem.
no problem. Then let's see the probability which I was talking about. Since we have to already always the probability of selecting any individual item from the stream has to be 1 by n. So let's see if it is still there or not. So when I am at index 0, I have only one option. So it seems that the probability is 100% of selecting index 0. Then if I come at index 1, the probability of selecting index 1 is 50%. Now if I come at index 2, the probability of selecting index 2 is almost 33%. And if I come at index 4, it comes out to be 20%. But the probability has to be, uh, I guess, 1 by n, which is 1 by 4, which is 0.25. But it seems we are violating this case where the first index has the probability of selecting the probability of selection of first element is 100%. The probability of selection of second element is 50%, and it is going down. So how come the probability is actually 0.25 or 25%? Here comes the main part of the uh, reservoir sampling, where uh, we were only taking into consideration the probability when we were choosing the particular value at that index. But we also need to take care of the fact that when I have gone across the index, there is a high chance that we don't select or replace the answer uh, which we took into the consideration in the previous iteration. So for example, if I am at index 1 and I choose and the random function generates the value 1, then I choose the value at index 1. Now when I come to index 2, let's suppose the random value does not generate 2, and it generate either of 0 and 1. So in that case, this value at index 1 is preserved. So this is why we need to take into consideration all the probabilities which are after the point of selection of a particular index. So this is why, okay, first let me complete the function part. If x comes out to be, let's suppose I am at iteration -1, then I will just change my answer to the value at that iteration, and then for each of the iterations I will just increment the okay. Then with the code part, let's see the uh, maths involved in this part. So the probability of choosing value at index I. So if I am at index 1, the probability of choosing index 1 is 1 by 2, or it will be 1 by I. Since if you go with the 1 based indexing, the index will come out to be 2, and we have number of choices to be 2, and the favorable choice is only 1. So the value at the probability of selecting the particular index at index I at ith iteration will be 1 by I. So this is fine. Now I come at index 2, and let us suppose the random function generates the in the a value 2 itself. So in that case, we are just replacing the answer variable to the value at index 2. But we need to calculate the probability of selecting the value at index I. So in that case, we have to again take into consideration the probability of selection of the next element, which will be, I guess, 1 by I plus 1. But since we are taking into consideration the probability of selecting index 1, so this will be 1 minus. Okay. Okay. So for index 2, this is the probability that we don't select index 2 and the value preserved to be the value at index 1. Again, if you come at index 3, we will be having 4 options to select from. So again, the value of the number of iterations will increase to be 1 by 2. And if they are n integers, then at last it will be 1 minus 1 by n. So this is very clear that this is an example of, let me just simplify it. It 1 minus 1 by I plus 1, so it will be I plus 1 minus 1, so it will be I by I plus 1. Similarly, it will be I plus 1 by I plus 2, and then at last it will be n minus 1 by n. So it is very clear that this is a telescopic product. So most of the values will be cancelled here. So this I will get cancelled with this I plus 1 with this I plus 1. And then here some n minus 1 will be cancelled with n minus 1. And the value which remains here is 1 by, and the last value which will be 1 by n. So, so the probability which here which we were getting to be 100% or 50% or 33% is actually 1 by n, which was the intended probability which we needed by selecting the particular item from the stream of integers. So does this make sense? Or is it too much maths?
Yeah, actually, yeah, that's what you're trying to prove, the probability, right? So we're always getting the same probability, even if we are choosing randomly and in the stream of those input, right? Yeah.
Yes.
And you have proven using this example.
Yeah.
Yeah. So
All right.
yeah, our intent here more is about uh, on the space complexity, trying to save the space complexity, not the time complexity, right?
Yes.
Yeah.
Since uh, in practical field, what will happen is the size of the stream will be too large to store it in any container. For example, a list of search queries in any Google or Facebook. The list of search query will be too huge for us to store it in any container and then retrace back from that container.
Makes
So
sense.
in that case, but we can iterate through the particular stream. That is not an issue. So in that case, we can iterate through the container, and with equal probability, we have selection of any individual item from the stream of integers.
Right. Yeah, makes sense.
All right. So this was all about this particular question, which was we need to select random node values from the linked list. And this was a particular question from Leetcode. Let me jump question. Okay, this is 382 linked list random node, where given a simply linked list, return a random nodes value from the linked list. And let's see what we have. So first we are given in the constructor part, we are given the pointer to the head node, and then for the get random function, we need to return one of the it is, I guess, stated. We need to return one of the values of integer from the linked list itself. So let me just code it up again. So I just assign the height and
So Abhishek, in this problem, we are not going to use that reservoir sampling, right?
uh,
because we
In this
already know
problem,
the initial set.
this problem is exactly what is happening in the reservoir sampling problem. Since we don't know the value of the search query at first, so the size of the linked list we don't know at first. So this is why
I,
we need to
I
take
thought
care of. Yeah, go ahead.
I thought in the input example that solution sorry, in the input example it is already giving us 1 to 3. So we don't, so you're saying we don't know the size of the list?
Yeah, yeah. See, the follow-up part is stated there. What if the linked list is extremely large and its length is unknown to you? So I am solving this part of the question.
Okay, okay, got it. Yeah, sorry.
Yeah, no problem. So, so in the constructor part, I just assigned the head pointer, and now in the get random function, we need to return one of the values from the linked list. So just uh, implementation where I will assign the value. So as I mentioned here, uh, I'll start the answer from the first index itself. Otherwise, it may happen that no, I guess that's not an issue. Since if we start from the first index, since it has a probability of selection to be 100%, so it will always choose the first index as an answer, and then it will iterate through the stream. So no problem. And then iteration will be 0. I add pointer 0. Uh, I can just take it as a temporary pointer, and then no start.
Yeah, Abhishek, could you come closer to the mic possible?
Yeah, sure.
Please, yeah.
So list, I've just assigned it to a temporary pointer, and then I will just increment the iteration counter first, and then I will generate a random function, and I'll modulus it with the iteration. So it's just a C++ implementation where I will be restricting the value from 0 to the value of iteration -1. So if this value comes out to be iteration -1, then I will assign the value of answer to be the value at that node, and then temp equal to temp dot next, and at last just return the final answer. So this is what we have to do here, I guess. First declare a answer variable, it register. I've just incremented, then I've taken a modulus if it comes out to be -1. Okay, let's run the code. All right, so it's working fine. Just let me submit. I don't think there will be any issue. Okay, done. So this is what this question was all about, where we were selecting one of random nodes from the stream of integer, and here the stream of integer was a linked list, and we were just given the head pointer of the linked list, but we had to choose any of the values from the stream at equal probability. So that has to be kept into mind while coding up the solution part. So this is one of the questions of the tag reservoir sampling from Leetcode, and the next question, which was from Leetcode and was tagged under reservoir sampling, was random pick index. A similar question
But the
from
one question in the previous, right?
yeah
But we're doing end time. Like if it is a list, then we do till that end of the node list.
yeah
We're not breaking up our answer, right?
no, if uh, if you break it in between, then For example, if you break it here itself, then this telescopic product part will not get cancelled out, and the probability will not come out to be 1/n.
Okay, yeah, yeah, yeah. Okay.
Yeah, that was one of the points. Otherwise, if if we have too much of space, we can directly copy it into a container and then generate a random variable, a random integer from 0 to n-1 and directly return that value. So that was all about this one. Let me jump to next question.
So then if it is a list is very big, then we'll be doing till that list, I think,
Yeah.
because of the probability constraint.
Yeah, and the space or the memory constraint as well. We can iterate through the list, but we cannot save the list somewhere else.
Yeah,
Does
because the
that
list
make
might be
sense?
very huge, as you're saying, right? Okay.
Yeah. Imagine it as a search which you do in Google. So if you search a particular keyword in Google, there will be uh, tens or thousands number of pages with that search result. So you cannot save each of the particular search results in a separate container. But what you can do is you can iterate through all the search uh, in the container. And that was only the question all about of selecting one of the items in the search space.
Hmm.
So,
Yeah.
Abhishek, if in that first problem, if there are a million numbers in the list, uh, and if I'm getting only if I'm doing get random only 2 times, will there be any chance that millionth number is gonna be printed or returned?
Yeah, it will be, I guess. The probability of selection is always equal. So the probability of selecting the first element and the last element will always be same.
Uh, yeah, but I didn't understand that part where we are iterating only uh, till that iteration.
No, we are iterating through the whole stream. So we are not iterating until an exact point here. Uh, so when I was at index 0, I was just generating all the index which I could have chosen if I started from 0. So when I was at 0, I had only one option. Then when I was at 1, I had two options to select from. When I was at 2, I had three options to choose from. When I was at 3, I had four options to choose from. So so you are not breaking at any point. You are iterating through the whole stream, and then if one of the values is selected, which will be since at zeroth index, if none of the values is selected at all the index except the zeroth one, since it has 100% probability at first, it will be always stored as the answer if none of this is actually stored or the value is not encountered, which is directly equal to the index one. So it's actually little bit hard since all of this is involved, but if you if you derive the solution in pen and paper, it will be very easy to
Thank you, Abhishek.
understand this. No problem. So the first problem was just the direct implementation of the explanation, and in the second question, what it is given is we are given a nums array or container, and we have to select one of the index where a particular value is there. So if the value which we have to choose is 3, then we have three options to select from, which is 2, 3, and 4. And if I had the if I had to select number 2, then I had only one options to choose from, which is number index 1. And if I had 1 to choose from, then I had only one option. So again, the solution will be same as the previous one, but only we have to take care of the particular value of the particular value which we have to choose from, which is the target variable here. So the same it will start from zero, iteration will start from zero, and we start from the zeroth index and then traverse through the whole nums array, and then if uh, the value at ith index is equal to target variable, then I will first increment the iteration, and then I will generate a random value from 0 to number of iterations, and if the value x comes out to be the mm, value which I had to choose, then I will just take that as an answer, and then finally I will return the answer. So let me just declare the answer variable, and that's done here. So in this question, what is actually happening is if the array is 0, 1, 0, 2, 3, and I had to select the target variable is 0, then the number of index which I had to choose from is 1 and 2. So I was just incrementing the iteration variable only when the value at the particular index comes out to be the target variable. And if the randomly generated number is the randomly generated number is equal to the iteration index, then I will just assign the index to the answer. And the return statement, you can assume that any given target number must exist in an array, and I had to return the index of a given target number. Okay, so here I have just assigned the index, and then I am returning. So let's check if this comes out to be correct or not. Hmm. So containers in C++ have size for determining the size of the input array. And okay, it's accepted, and just check. So it's just the extended version of the previous question. Okay, it works fine. So this
Like,
was
are
all
we
about.
assuming it is already sorted list, right? Or
No, there is no problem if the list is sorted or not, since we have to take into
only
consideration
random?
only the index at which the target value is. So
Yeah,
if
the same as previous guy.
yeah,
Yeah, yeah.
yeah, 1, 2, it will be 1, 3, then 6 and 7. So I had to choose only from these four variables. So I was only increasing the count when the value at the index of the container is equal to the target variable. So this was all about this topic, and Leetcode has only these two questions in the tag reservoir sampling. Uh, yeah, only two questions in reservoir sampling part. Now, the main focus of reservoir sampling uh, was to choose k elements from n items. So we were just choosing one item from uh, n elements, and the value of n was not predetermined. So the main aim of reservoir sampling was to select k integers in a stream of n integers. So how we can approach this question? So the first approach will be similar of the previous kind, where we will be first storing the n integers, and then we will be generating numbers from the range 0 to n minus 1, and if and we'll be generating k integers from 0 to n minus 1, and if uh, and then we will be assigning that integer into the answer which we have to return. Since we have to return k integers, so we have to return a container of size k from the function. And I don't think this question is on Leetcode, so uh, no problem. So the first approach will be similar, where we will be choosing x integers, and I will tell why we are choosing x integers and not k integers. First, we have to store the stream. So store the stream, and then choose x integers. So we are choosing x integers. Now, why x integers? Imagine the first random, the first the random function returned me zeroth index, and then the second random index, the function also returned me zeroth index. So I don't need this zeroth index again. So this is why I have to check again in the kth integer array, where if the zeroth element is already present, then I have to discard this random function. This is why we are generating x integers and not k integers. Now, this x integer will actually depend on how the values are generated randomly. So, in the worst case, what can happen is in worst case, this value of x can be x square k to the power 2 or k square. Since imagine I am no, it can actually go really large if I am generating zeroth index again and again. So this is why the value of k will be will be exponential. Since if imagine if the random function generates only zeroth value, then we really don't have the we don't really don't have k integers again, and we will be storing only one of the values here. So this is why this approach will fail, I guess, here. So also, since we were storing the stream, again, there is a problem with memory. And then this is again a big problem where if the randomly generated variable is generating the same value again and again, which I think it will not generate every time, but it might happen. So we can't say. So the value of choosing k integers can go really large. So just skip this case. Now coming to the second uh, approach, where again we will be using reservoir sampling. Now before going through the reservoir sampling again, we will be having two cases, which will be with replacement, where we can choose same element again and again, and there will be without replacement. So the with replacement part will be exactly same as the previous solution, since here what we can do is we can generate an index and then repeat this process k times, and that's not an issue, since with replacement is allowed even if the zeroth index is generated k times, no problem. I will store the k elements, and then I will return back the vector of k integers. Now the main focus is on without replacement, where we were facing some issues in the approach one part, where if the same integer is generated again and again. So in without replacement part, there are two parts. So the first part is the index from 1 to k, and then the second part is from index k plus 1 to n. So imagine I have a container of I already have a container of size k, and then I will just assign all the values in the stream from 1 to k directly to my answer. So array of I is equal to nums of I. And then this will be for the first part. Now for the second part, which will be from k plus 1 to n, I have to, now here comes the main part where from k to n, okay, so here I will generate a random variable, and the random variable has to choose from 0 to that particular index. So it will be again, since it is 0 based, I have to convert it into 1 base, so k plus 1. And now in the previous question, we were checking if the value of x comes out to be the iteration itself. But here, if the value of x comes out to be, okay, so value of x is, if the value of x is less than x, then I will swap the values of array at x and I. Okay, so this is what we had to do in the second part. Now, also, since we had to keep in mind the equal probability part, and since we were choosing k elements from n, so the probability of choosing ith element has to be k by n. Okay, so in the second part, if the random value comes out to be less than equal to k, then we will swap at the particular index and kth value. Now, that's okay. We have solved this question, no problem. But what about the probability part? So again, we have two parts to calculate if the probability comes out to be equal or not. So let's do the second part first, which will be easier, I guess. And probability of selecting I value, and the value of I lies from k plus 1 to n.
Hey,
So
Abhishek,
yeah,
may I interrupt you? Yeah.
yeah, no problem.
So in the previous function, okay, the for so you are taking x is equal to rand of modulo k plus 1. So will the x value always not be less than or equal to k in that case?
Should go to k plus 1, right?
Yeah. No. It will go up to k, and I had to choose from 0 to k minus 1, since I was assigning from 0 to k minus 1. So this rand function will be generating values from 0 to k, and
K plus 1
if,
it should be, right? Because you are taking the mod with k plus 1. Okay, no, remainder will be 0 to k minus 1. Okay, fine, fine.
and I had to swap only if the value comes out to be 0 to k minus 1.
Okay.
And okay, it has to be I plus 1. Okay, now it is.
Okay, no problem. Yeah, thank you.
Yeah. So, for the second part, imagine I am at kth index, and the value comes out to be from 0 to k minus 1. But the total number of values were k plus 1. So if I had to select value at index I, then total number of options which I had was k. No, the total number of options was k plus 1. And if I had to choose the particular index, then I had to get k values out of it. So since we were generating values from 0 to k, and if the value comes in 0 to k minus 1, then only I will swap. So this was, we select the value. Now imagine I have already swapped it. Now I go to the next iteration, and the number of ways so that the next iteration will swap again with only this value of the previous index will be has to be 1 by k plus 2, I guess, since we in the next iteration we will be having one extra point of choosing it from the random variable, and then I had to do this 1 minus, so that uh, this probability will be same as not choosing the particular index for the next iteration, and then this will again continue as it was in the previous explanation part, and this will be 1 by 1 by n. Okay, so again, if you calculate this part, it will be k by k plus 1. Then this will be k plus 1 by k plus 2. And then last it will come out to be n minus 1 by n. And then again, this is same as same telescopic product, and all the terms will get cancelled. And at last, the first term and the last term will remain, which is k, and the last term, which is n. So the main intent was to get the probability of k by n, and which was our main aim. And at last we got k by n, but only for one of the parts, which is from k plus 1 to n. Now we have to again check the probability is again k by n for the first part. So now the value is from 0 to or just one base indexing is 1 to k. So the probability of selection of values from 0 to k is same of I guess the probability of not selecting I guess the probability of not selecting these values which are from k plus 1 to n for that particular index. So if I am at kth index, and at kth index I will be having 0 to k options to select from, which will be uh, I guess k plus 1, but I don't want it to select 0th index. So if I don't want it to select 0th index, the value will be k. So this will be for this part. Then again, for the next, if the value comes goes to be k plus 1, then for k plus 1, I will be having k plus 2 elements, and I don't want a 0th element to choose from, so I will be subtracting one element from the total number of possible elements to choose from. Again, this will go, and then at last it will be n minus 1 by n, following the general pattern. So again, as previously, this all the terms will get cancelled, since k plus 1 will get cancelled, k plus 2 k plus 2, n minus 1 will get cancelled, and we will be left with k by n. So for both of the parts, for the first part, uh, we have the probability k by n, and for the second part, we have probability k by n. And this was our main aim, to choose k integers in the stream of n integers with equal probability, and the probability has to be k by n. So a lot of maths was involved here. Any questions?
Yeah. So a lot of maths involved. That's right, but that is the way to explain and prove it, right? Yeah. So that made
Yeah.
sense because you had to prove with both the parts, right? So the
Yes,
probability
yes,
has to be k by n, and yeah,
yes,
it was good. Yeah.
yes. If you study this concept properly, all the concepts of probability will also be revised. And
Yeah, that's right.
to yes, this questions was recently asked in one of the interviews. So when I was doing the lead code problem, I just remembered that it was just asked. So I thought of explaining it today.
Okay, no, that's good. So you mean to say this question about k by n probability, not the one which was in the reservoir sampling in the Leetcode, right?
Yes, the main problem was selecting k integers from the stream of n integers, and the main problem of reservoir sampling is actually selecting k integers from the stream of
Yeah,
n
that's a
integers.
standard algorithm everywhere you'll find.
Mhm.
Yes, selecting one integer out of n integers is just a simple form of that randomized algorithm.
Okay, nice to know about this thing, and it was a great explanation. Yeah, yep. Thank you,
Yeah,
Yeah.
thank
Abhishek.
you.
Yeah. Any
Thank you.
any questions, guys?
Yeah, was awesome.
Yeah.
All right, I will just stop sharing.